Hi class, this lecture is going to be on Feynman diagrams. We have already covered 7.1 and 7.2, so this is the final piece of 7.3. Previously, we've already discussed like the subatomic particles and their properties. We've discussed particles and antiparticles, quarks, antiquarks, leptons, hadrons, mesons. We've talked about bosons, baryon number, charge, strangeness of quark, quark confinement, how they're always next to each other. You can't find them alone. And we're going to use all that and apply it in diagramming to help us understand which reactions can actually occur, both using the conservation laws from the past and diagrams that help demonstrate what they look like, or a convention of what they can look like. So today's class, let's see, we've technically already kind of done the use of concepts of conservation. We've already discussed four fundamental forces. And we're going to really focus on the exchange particles, the bosons, and how they are mediating the four fundamental forces. We're going to draw Feynman diagrams, and we're going to apply conservation ideas at the vertices of the Feynman diagram. So that's our final push in 7.3. We're using the data booklet from 7.3, subtopic 7.3. We're going to need to identify all parts of this, the charge, the baryon number, the lepton number, and then all the four forces. So let's do a warm-up, kind of talk about the four forces. We have strong nuclear, electromagnetic, weak nuclear, and gravitational. The examples, when we talk about strong nuclear, we're looking inside the nucleus. So this is holds nucleus together. The electromagnetic is the force between electrons and protons. The weak nuclear is specific to radioactive decay and fission. And gravitational is with stellar masses, or all masses, but specifically, we can look at like our solar system. The range, well, strong nuclear is inside of the atom, so it's between the protons and the neutrons inside the nucleus. So this is very, very short. And what I mean by short, it's like something like 10 to the negative 15th meters, which may be useful to remember. That's about the radius of a nucleus. Electromagnetic, between charges, so that's infinite. Weak nuclear, it's even shorter, and that is like 10 to the negative 18th meters. And that's within the radius of a quark, or the approximate radius of a quark. And then gravitational, between masses throughout the universe, so that's also infinite as well. The strength, it's written in this way to be recognized as this is the strongest. So this is like number 1, this is second, this is third, this is fourth. And this is the point where I'm going to bring up how important your data booklet is that your data booklet's already written, but it's written from the weak, or the weakest, to the strongest, which is strong. So something to note is if you ever have a question, it's right there in front of you. They also tell you of all of the particles that are experiencing the forces, as well as the particles that are mediating, the exchange particles. And that's what the next two questions are going to be. So I might leave my data booklet right there, because these questions will come up. So within the strong nuclear force, we're looking at exchange particles involved in the exchange. The exchange particles involved are the same thing as the particles mediating. So those are the same. So when looking at our strong nuclear, in our data booklet, we can see that it's the gluons, right? That's what holding the nucleus together. For electromagnetic, in our data booklet, it shows this symbol. We've been drawing the symbol like this. I kind of do little Y's. Whether or not, you don't need to know that. Either way, These are the particles that are mediating the forces. So whenever it's asked for which exchange particles are involved, those are the particles that are mediating the forces. So for strong nuclear, in my data booklet, I can see that it is a gluon, or gluons are mediating that force. For electromagnetic, I see this symbol in which there's two ways to draw this. One's with that little loop, really making that loop more apparent. I tend to kind of draw more of like a Y, although I believe the loop is the correct way. Either way, you know what that means? It means photons. That's what that means. So photons are the exchange particles for the electromagnetic force. The weak nuclear force are these bosons. They're W plus, W minus, and Z, which is a neutral boson, depending on if we need to, if there is a charge being transferred in the radioactive decay process. A gravitational exchange particle is what we call the graviton. This is weird because we never really brought this up. We more so taught the Higgs boson, which kind of gave things mass inside of this Higgs field, which we actually experimentally observed. The graviton is still a theoretical particle. It's kind of our placemat for the exchange particle for the gravitational force, since we are still kind of putting the pieces together for that. So something really neat is that there are still things that we're learning as of now, right? This is all pretty darn new. I mean, what the experimental evidence for the Higgs boson was 2012. So, in the next 20, 30 years, who knows what we are going to find out. And as we move forward, where the particles that are exchanging, let's do this like glue, are exchanging the exchange particles. These are like the particles they're experiencing. Oh, it doesn't want to save that. Okay, what about this blue? That's better. And this is where, when we have the strong nuclear, we're looking at quarks, and we're looking at gluons. For electromagnetic, we're looking at all charged particles. And for the weak, we're looking at quarks and leptons. And for the gravitational force, we're looking at all particles. So it might be strange, though, too, considering our lack of full understanding of the gravitational force, that all particles, including photons, which technically don't have mass, also are subject to a gravitational force. Yeah, and you'll notice that actually I have written things below. That's because this was a mistake. And so I'm going to chop back in and do my best to kind of fit this in. But if you see this later in the video, you'll see that these aren't highlighted because I accidentally flipped these in the next part of the video. But I fixed it now, so just know that it might not look the same later. So what are these exchange particles, these gluons, these W bosons, these gravitons, these photons? Well, they help us model the interaction of the four fundamental forces. Now, what's interesting is that these forces occur no matter what, no matter if there is a photon, no matter if there is a gluon, a graviton. They kind of show up when they need to. So if electrons are approaching, there's an electric force that's going to cause a repelling. You're going to see a photon show up in the middle, and it shows up out of nowhere. Where did this come from? And this is what we give. These are called virtual particles. Most of our exchange particles actually are virtual, only if they kind of fly off, we're able to detect them, that they're not. And these are really weird instances of our understanding of physics, because virtual particles can pop in and out of a system to mediate a force. So it's a very weird concept that we've applied. We're like, wait, how the heck do these forces really occur? And it's like, well, it can only occur if they kind of show up and then disappear. And that can only happen if they only show up and disappear in an infinitesimally small amount of time, because there's this really strange concept with Heisenberg's uncertainty principle with energy and time, and that energy can show up, but it must be taken away at some near time interval. And I mean, I'd say near, I mean like really near. But I'm going to stop talking about that because it's very strange, and we just need to know that they do exist, strangely. So we have identified in the standard model that we have the quarks, we have leptons, we have these exchange particles, these bosons. How can we fit them into a nice diagram to show these interactions occurring? And the answer is in these Feynman diagrams. Here I have two GIFs of two different interactions. We have a electron-electron annihilation, or pair annihilation, and then we have a muon decay. And we might not know what's happening here. We know that there are quarks and leptons and things like that. How do we draw these accurately? So let's get into the drawing conventions. In IB, we tend to draw space and time in this way, where space is in the y-axis and time is in the x-axis. Also know that space is generally just a scalar distance. It doesn't have to do with an x, y, or z coordinate. So it's just movement forward, backwards, etc. It's also good to know that sometimes these axes can be flipped. So you might randomly, and IB could even do this to you, but just be very careful. If you might see it with time in the y-axis and space in the x-axis, in which you just flip your screen, or flip your screen, distance learning. Flip your sheet of paper so that you can see it in time and space. And then we need to be able to draw some symbols on there, like we saw above, right? We see some arrows, we see some wiggly lines, we see some that's kind of like dotted lines. And here are the 4 or 5 symbols that we're going to use. So the first one is some arrow moving forward. And when I say forward, it's moving in this direction. I'm going to say that's forward in time. And that's specifically because time was in the x-axis, so I'm trying to kind of match that. So when it's moving forward in time, these are our particles. Those are our quarks, our baryons, our mesons, so forth. But when we are going backwards in time, uh-oh, did I just say that? Yep, there are particles that can go backwards in time. Which particles do you think they are? You guessed it. Antiparticles. So there are anti-quarks or anti-baryons, or anti-leptons, so forth. And then we have this wiggly line. So this wiggly line, there are 2 things it could be. Most likely is it's going to be our photon. It can also be our W, or W boson or Z boson. If it's not virtual. Now, IB sometimes doesn't get this right. So just know that, don't worry too much about this. I think we're going a little bit too hard on these Feynman diagrams. Just know that it can be a photon, but it also could be a W or Z, if not a virtual, but they get that wrong sometimes. This is a gluon, and this dotted line is technically the correct way to draw your W and Z bosons when virtual. But you'll see them kind of flip between the squiggly and the dotted lines in IB problems. Just don't worry about that too much. All right, let's look at some examples and see if we can make sense of these diagrams. When we look at the space-time axes, we want to start from the beginning and move towards forward in time. So I would start looking at these 2 electrons moving forward and kind of seeing how if they do interact, and then looking at the vertices. And it's important to look at the first vertex and then the second vertex. So I might want to focus on this one first and then the second one, but sometimes it's not as important, but I still think to keep that in mind. So we see a photon being emitted and a photon being absorbed, but really what we also see is the electron being repelled and this electron being repelled. So this is just the repelling of 2 electrons due to the electromagnetic force. And the photon is acting as the virtual particle, virtual exchange particle. Let's look at the second one. Well, it looks a little similar. I also want to start forward in time and start like here and kind of move up. But you might say, whoa, that's weird because my electrons are moving backwards in time, but don't really worry about that. Those are just conventions for recognizing what is a particle and what is an antiparticle. So still move forward in time. Don't try to watch it. Don't go towards the arrow. Always go forward in time in our view. And then we have a photon interaction, and there's a change in direction. Doesn't matter which way you look at it, there's still a change in direction. And these are 2 positive charges. So of course, this is the same. This is still the repelling, I'll make sure you can see it, of 2 positrons due to the electromagnetic force. All right, third one up. Again, start from our time, move forward in time, and I see a photon is moving forward, and then, interesting, we have an electron being made, and we have a positron being made. And this is what we call pair production. Where a photon produces an electron and its antiparticle. Now, similarly, if we go in the opposite direction and we see an electron moving forward and a positron, kind of coming out, but moving forward, we end up with a photon. This is called pair annihilation. Ooh, how am I going to spell it? I think I spelled it right. Forgive me if I didn't. And this is where, and really this can happen with anyone. In this case, it's an electron, but you can say a particle and its antiparticle. Annihilate to produce a photon. Because a particle and its antiparticle are equal and opposite in every way. So when you combine them together, you just pretty much create energy. Or the opposite, energy can create both a particle and its antiparticle. All right, the last one is, what does this reaction look like? Time is moving forward. So I'll start moving down. I have a down, changing to an up. And then I notice that my W minus boson transfers and produces an anti-neutrino and an electron. And I remember when you have these two, right? When you have these two, this normally means what? Beta minus decay. So we haven't really been telling you, but beta minus decay and beta plus decay is not the changing from a proton to a neutron or a neutron to a proton, but it's actually changing a quark, one quark to another quark. And then, knowing the composition of a proton and a neutron, it's creating what? DUD to UUD, right? So we're going to have a lot of practice with that. Now in this next practice, I'm going to give you guys the front seat. I want you to try and draw this. For each example, draw its corresponding Feynman diagram. An electron emits a photon and keeps going. I will start you off with just drawing the space and time axis. Sometimes you might actually see a problem that doesn't have an axis, in which you just have to assume space is y and time is x. All right, I'll give you a minute. I want you to do this one. Don't forget to pause the video. All right, so I've got my electron moving forward in space and time, and then it changes direction, and it's still going forward in time, just changing direction in space. Now, it doesn't actually matter how you draw your photon. I wouldn't draw it backwards. I would still kind of draw it kind of either going straight up or slightly forward, but it doesn't really matter. And a common mistake you might draw is if you would have accidentally drawn the electron going like this, in which then it would be going backwards in time, and then it wouldn't be drawn as an electron anymore. So just be careful about that. This is the correct way to draw it. All right, now I'm going to give you the chance to draw these next two. I'm going to pause the video. We have a positron that absorbs a photon and keeps going. And then we have an electron and a positron annihilate to produce a Z boson, producing a muon and anti-muon pair. I'm going to pause the video now. All right, I'm back. I'm about to show my drawing. So for positron absorbing a photon and keeping going, here it is, the same as the electron absorbing a photon, just the time is going backwards in time. It's the most important. And for the next one, we had to draw kind of two vertices in which an electron produces a positron, one going forward in time, one going backwards in time. And the Z boson is the exchange particle, and it exchanges it with a muon pair as well. One thing to note here is that we can notice that this positron and this electron are together, as well as this muon and this anti-muon are also together. That's because when working with particles and antiparticles and neutrinos, these are called families, where electrons and electron neutrinos tend to stay together, muons and muon neutrinos tend to stay together, and the tau electrons and the tau neutrinos also stay together. Okay. So we've got some practice. Some important note, kind of like I said before, the particles are not actually traveling in straight lines. It's just a convention. They're just moving some direction forward, some direction backwards. So they're only meant to show forward or backwards. Also, when drawing Feynman diagrams, you cannot have exchange particles interacting. You cannot produce two exchange particles. We draw them separate. So just know that that's not good, and that's our good one. All right, now we're going to do some examples with conservation laws. We're going to use what we know from before with our conservation of charge, baryon number, lepton number, and strangeness to identify if this is possible or not, or if there's any holes that we can determine if something is missing. So let's start with the first one. We have our first interaction where we have an electron neutrino comes in and meets, and so it comes right here, and it meets this vertex. Now, this is important. This, up until this vertex, this is our before. And then after it leaves the vertex here and here, that's our after. So whenever we're seeing before and after, it's important to know that to not make any mistakes in our conservation laws. So I only see one thing coming in. I see my electron neutrino. That means there's nothing else before. Electron neutrino does not have a charge. It doesn't have a baryon number, has a 1 lepton number, and it doesn't have a strange. What about after? Well, we have our electron and our W plus boson. And our charge for our electron is -1, W plus is +1. They're not baryons. We have a +1 lepton number and 0 for our W plus, and then there's no strangeness. And so this is, yes, this is possible, because this is equal to 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, so this is possible. I want you to do this on your own. So at my vertex, I've decided my before and after. I've chosen my particles, and then I've checked my charge number, baryon number, lepton. And I saw that in my charge, it should not occur. This is not possible because there's no conservation of charge. All right, move into a slightly harder one. Now we're getting to multiple vertices. And in order to do that, we need to separate this by vertex 1. So it's right here, vertex 1. And vertex 2. So I might say, okay, let's drop this. So let's do it in red. Right, this is before, and this is after, and this is before, and this is after. and I do it as two separate tables, and I check to make sure that the conservation laws work for both vertices. All right, go ahead and do this. I'll pause the video. Something to note, this is a W plus boson, so you'll need to know that when you put it in right here. Pausing it again. All right, so I've finished. And what do I have? I have the first vertex checks out, the second vertex checks out. So yes, this is possible. All right, so we're almost done. I have one last example. We have identified the exchange particles in our standard model. We've identified which forces they relate to and which particles experience in them and what particles they actually are. We've discussed what exchange particles are, that most are virtual particles. They pop in and out of existence. And then we've looked at how the diagrams are drawn to showcase all the different types of quantum interactions that can occur. We talked about the conventions in order to draw them. We've been able to identify what each interaction looks like, how to describe them, and then we've drawn them more, and then we've identified conservation laws with them. Now there's one more thing I want to include, and it has to do with a weak force versus strangeness conservation. So number one says draw the arrows for the U and the D in the diagram, although the U should have a anti-U on top of it. And so notice how in this picture the time is actually going up, right? Time's in the x-axis or y-axis, and it's normally in the x-axis. There we go. We got to be aware of this. And so I would draw my time for, actually let's do it in red so it's more visible, for my anti-up going backwards in time, or my down is going forwards in time. The second question is to identify which of the four fundamental forces this diagram is representing. So let's make sense of this diagram first. As we go forward in time, we start off with this strange quark. The strange quark decays into an up, which releases an anti-up and a down through some sort of decay process. We're dealing with quarks, so we can either be dealing with the strong nuclear or the weak nuclear. But how do we identify the difference? And it has to do with when strangeness is conserved. So strangeness is only conserved in strong nuclear interactions. If strangeness is not conserved, then this must be the weak nuclear. So when the strangeness is not conserved, let's highlight that, then it must be the weak nuclear. And so this must have a W or a Z and a W or W plus or W minus. And if we looked at the quark composition and the charge in the U and the D and the S, we'd be able to identify that. All right. Well, that sums everything up. I will see you in class.